Start recording. So this semester we are going to give the course interchangeably with Erol Şahin, and actually I'm going to give the Monday lectures of 2 sessions, and Erol is going to give this Wednesday and Friday sessions, but in this week we made a switch. I'm going to try to be more telling you about practical parts of the operating systems. But today, let us talk about the history. Echo, I don't know if everyone is suffering about echo. Maybe I can try to click some places. I don't know. Okay. Okay. So please ask questions in the chat, or if you like to use your microphone, it will be glad, because I can feel that you're human. You can raise your hands if you like, or if I ask you a question, you can directly turn your microphone on and talk. A little bit of history, actually. You know a little bit about this from the Introduction to Computer Engineering course, Department 111. The first computers, or the machines that we can call computers, goes back to 40s. And since they were targeted machines for solving specific tasks, like just like population counting and so on, they used to have single program memory. Okay, so the ultimate purpose of them is just to load the program, execute them, and output the result. So mostly the operating system wasn't there, but just a basic I/O system, a single loader, loading the program into memory, executed from the start of the until the end, and then terminate. So what they had is, however, of course, they need to interact with the peripherals, the input devices and output devices. So what they did is simply providing some libraries, and those libraries like input something from tape, print something on printer, and so on. So basically it is just a library, a set of libraries interacting with the peripherals. You compile your program into, or you add those libraries within your program, and at the end you are going to execute them in the machine. However, it didn't last long, so we have in 60s we started using the real operating systems, but they were simple batch systems. So basically, I believe you have seen this punch cards before. So it is just a single line of program. Okay, so this program is just each column here stands for a column of the code, so that so it is actually some compact form, I believe, in order to have economy of cards, because those cards are actual cards. They put multiple lines into a single card. So that's why this is just a single line of code having some, I'm not sure about the language here, but it looks like Fortran. So it's a 4J is from 1 to 100, next line 425T, blah, blah. So for each line of code or each couple of statements of code, there is a punch card, and those punch cards were just sequenced into some bunch, and it's batch actually. This batch is fed into the computer, and the computer will read that and put that program into a queue. Okay, so this is the operating system's art actually. By that time, there is a queue of programs, and punch cards end up in some program in the queue, and the operating system is simply fetch next program in the queue, execute until end, and delete it, fetch next program. So it is a simple queue-like operation. And actually it was quite difficult because there were typewriters, and people were writing those with typewriters like this way. So punching requires some mechanical, actually they had motors, but some mechanical operation. And if you clicked a wrong letter, for example, you have to throw that card out. So it is the batch system is actually needs to implement a queue. So a queue of programs. And what batch system does is having that FIFO queue and in a loop fetch, execute, and go to the beginning. So it is just a fetch and execute loop. But during that, of course, we have the same libraries that are interacting with the peripherals and so on. So what you do is you supply a punch card, give it to the operator. Operator will fed it into the operating system, and at the end, you go grab a coffee, and after a couple of hours, when it's your time, you get your printout, and you will see some compile error. Okay, so you correct your punch card and try again. So it was a time like that that I don't had to, I didn't suffer. I was younger than that, but if I were like 10 years older, I might have done that. So this is batch system as it looks simple. The hardware was complicated, so it was the early stage. But we have a serious problem here. The problem is when this one is making I/O operation, all others wait, okay? Or waiting for something, assume there is a sleep, for example. I'm not sure they used to have the sleep call, but if one of them having the CPU sleeps, everyone will wait. So that means during this period, the CPU gets idle. So if you look like that, we have program A, program B, program C, and idle. So in the batch, we have such a graph. During I/O, our CPU gets idle. Then here, at this moment, it exits so that the next one, assume next one is C, gets CPU and execute like that, and it exits and then gets B. So as you can see here, all those idle parts are simply wasted because your CPU is over there. It is connected to the electrical circuits, but it is not doing anything, but the programs are waiting. Okay, This is what we call the CPU utilization, and it's a bad utilization because everyone waits. Even though there are runnable processes or runnable programs in the queue, you just do nothing, which is not acceptable. So the idea is instead of that, can I do something more smarter? So this shows how they looks like. So this is my job description, and first says programming language I'm using is Fortran. So the Fortran program here is compiled. As I said, there is a compiler. You can learn about it 1 hour later, for example. Then you load your program and execute that. And you have to provide input in the batch, in the punch cards as well. Okay, the program and input are put into the punch cards here, the data of program, and then it is like in Linux we have this standard input is coming from input redirection, so that we refer data as this less than sign and so on. It is provided here. It is fed into card reader, input tape, operating system, output tape, printer, and you will get the result. And the operating system is simply a queue processor. Fetch execute. Okay. So we have the spooling concept. So this queue of programs are put into this spools, and operating system fetches next one and execute and output disk, putting all of them completed once here, and there is a printer taking from output and printing it. So in order to solve this problem, they came up with this multi-programming idea. So in the especially if you have these asynchronous devices, I/O devices, and some need for waiting for operations, we can have this unutilized part taking advantage of multi-programming, and then they came up with this idea. So let me just draw that on a wait queue. So what if I can do this instead of a single queue? If I have multiple queues like that. Okay. So I have 3 queues, and they used to call that the virtual CPU. So each is having a virtual CPU. But actually, this is not correct. So this is just an illusion. There is no virtual CPU, there is no CPU, but there is only one real CPU. So what real CPU does is it divides the execution into slots. So it executes from queue A, B, C, executes A for some time, then for B some time, then for C some time. Okay. So in this way, it is going to divide the CPU power among the queues. So I have A1, A2, B1, C1 here, A2, B2, and it goes like that. So the timing will be now A, B, C, A, B, C. And if A, wait here, it will be B, C, B, C. Then A wakes up, A, B, C sleeps, A, B, then C wakes up, and so on. As a result, as long as there is an item in other queues, if other queues are not empty, so we have a better utilization. So there is no idle periods of CPU. Unfortunately, I programmed for such a machine in my summer practice in MTA, Maden Teknik Arama. It was very old machine. Even for 90s, it was ancient, so it is 4331, I still remember. So we didn't have punch cards, thanks God. But we had terminals, but in the terminal, when you write your code, you submit it in one of the queues, okay? And you have to guess which queue is better, okay? You look at the queues, and if you try to estimate the other's completion time, and you submit the correct queue, and it is going to be processed, and output is generated in the same way with the batch system. So this whole concept is called multi-programming, because at any instance of time, multiple programs are in memory. Okay, depending on your virtual CPUs. Of course, this is not the only model of multi-programming, but this is something I am familiar with, okay? So this is the case of multi-programming. Actually, no, it doesn't need. If you have no user interaction, you don't need sleep. If there is user interaction, the simplest answer will be your desktop clock application. It needs to sleep so that it is going to show you the next time, okay? Some of the peripherals require polling. I'm not sure about these ancient machines, but so the thing is, you write some data, wait for a period of time, and you poll that, okay? Did it finish? Did it finish? Did it finish? And during that, you have to sleep. If you don't have a device or interrupt-based device, you have to poll, and during the polls, you may need to sleep. But it's a very good question. Yes, we need timing in such cases. In an interactive case, there are various scenarios, especially when you are attached to real-time clocks and so on. But during this course, you are going to learn that sleeping is not a good idea. Okay, at least in the chapters about synchronization, we are not going to allow you to sleep. Okay, so up to this point, everything is all right. Do you have any question? Any question? Curious about anything and so on? Okay, then I'm moving on. So this, okay. When you mean in the current operating system, yes, but there are multiple queues, but they are not in this strictly divided virtual CPU sense. They are for asynchronous operations. For each kernel thread, for example, you may need a separate queue, and the producers of tasks insert at the queue, and the kernel thread will process it. We have such cases. Or for each hardware device, we have a queue. Hardware device inserts in the queue, and the processor will process it. Network device, for example, they just insert into socket buffers, and the other layers of networking in the kernel will consume that. So we have many queues in a living operating system, but not this fixed interval, fixed size manner. Okay. No. We are going to talk about that. For implementing threads, you need queues. Okay, you can write that order. If you rewrite the sentence this way, it's correct. In order to implement threads, we need queues. Okay, so that CPU will know which one to take next. Okay. But these are good exercises about thinking. I like the way you think. The multi-programming is okay up to some sense, but if you have more contemporary applications, especially user likes to get feedback, we need interactive execution. So when I press a key, I would like to see the response. When I press enter, I would like to see the response. I don't like to go to the printer room and look at my output for an hour. Okay, so the when the terminals are invented, interactive terminals through serial lines are invented, and with the mini computers, we had this notion of interaction becoming important. So they came up with this time-sharing systems. In the time-sharing case, this switch between the processes or programs is asynchronous. So we have users interacting with the operating system. However, they are users. There is not only a single user, but multiple users. If you ever heard about MS-DOS, did you hear about Microsoft DOS, Bill Gates' first project? Okay, it was like that. Okay, single user. Okay, single user in front of the PC, and whole purpose of I cannot call it an operating system, but whole purpose of that program, the Microsoft DOS, is to serve him. Okay, so only that user's programs are executed, and the machine belongs to that user. Sinan Nefçi, our instructor, called it BIOS. So MS-DOS is not an operating system; it is a BIOS, basic I/O system. However, late 60s and early 70s, we had this problem. We have limited CPU and we have many users. And can we serve them interactively? And they came up with this idea of time sharing, so that we can share the CPU asynchronously. So when your program is executing, I can type something, and when it's ready, I see something, and so on. Microsoft directly, yes. If you mean that it was running on the hardware directly, it just provides a couple of software interrupts, and the programs are calling them. Okay, so it is closer to the actually batch systems. In order to do that, we need another mechanism. So in the next chapter, we will be talking about this, what we call the time slicing. So asynchronously, we will let users sleep and wake up, execute for a while, and the other one is executed. So the operations are completely asynchronous in the time sharing case. When I press a key, or let me start this way, when my program is waiting for input, it sleeps. It sleeps on a queue. Okay. When I press a key, it wakes up and says that I'm ready to execute. The CPU sees that, the scheduler sees that, okay, this guy is ready. So now it is in the queue, and the next slice is going to be given to that. And in this way, since most of the interactive programs are sleeping for their lifetime, so it is like, for example, VI or your favorite editor, whatever it is, Nano or Visual Studio, whatever it is, waits for like 90% of its lifetime. Only 10% of its lifetime, you are pressing something and it do actual something useful. So the editors are suffering for waiting for your input, okay? Because they are fast and you are slow, unfortunately. Do not take it personally, but humans are slow. So they simply wait, so that in this interactive scenario, multiple users in the same machine, same computer can use the CPU. But if they try to get this number crunching, CPU operation, matrix multiplications, iterative matrix solvers, etc., now there is a contention, so that they compete for CPU. So the time sharing systems take advantage of this interactive processes waiting a lot and trying to be as fair as possible among the others, CPU hungry jobs. They slice CPU into multiple users. So the interesting point in the history of operating system is this Multix project. It is multiple information. I forgot about that. Shame. This process by MIT, and it was very ambitious project. Okay, so they tried to find solutions to problems that are solved like in 90s, for example, late 80s, in the 60s. Okay, so some of the ideas in Multix came in life like in 80 something version of the Unix. So this concepts was huge, and the machines were small, so they have limited memory. So I am talking about kilobytes of storage used by all METI users. We used to have a mainframe, IBM 3090. I believe it is something like 128 kilobytes, or in the worst case, 1 megabyte of memory. So 1 megabyte memory is used by hundreds of users. Okay. In such a world, this ambitious project cannot be completed. However, it became an opportunity for a couple of guys you are familiar with, actually, which are Kernighan, Ritchie, Thompson, those guys, working in the project, and I believe they were trying to play a game, some command line strategy game, and in order to implement their game, they had this shrink down version of Multix, very simple subset of Multix. Only purpose is to make that gaming available. They wrote it in assembler, and just as part of their humor, instead of Multix, they called Unix. Okay, so it is, instead of multiple, it is some unique something. So they introduced this Unix in 70 in assembler. In 71, they tried to port it in high-level language. They didn't like the existing languages, so they introduced C programming language, which is successor of Algol and Pascal. And there were some attempts called B in the Bell Labs. Bell Labs. So they wrote it with C, the language they invented, and starting with 72, 73, etc. Something interesting happened. Those machines, the mini computers, they call that mini computers, which is like refrigerator size computers, were called mini computers, were delivered by with the VMS, Works Management System. People started, or PDP-11, I believe, they started installing Unix instead. And all of the, even the commercial operating systems were open source, so they start compiling their own version of Unix and using them in their mini computers. So Unix became popular in 78 a lot, so that most of the mini computers were running Unix. And it became quite important operating system, since most of the things like inter-process communication, the sockets, network interface, etc., internet implemented in Unix machines first. This is the slide for personal computing. I code some these 80 version computers. I used to have some Atari 800 XL, and it was time of Commodore 64. So the small CPUs fit into small machines, so they call it microcomputers by that time, with monochromic displays and so on. So such a machine had 64 kilobytes of memory, which is large for a single user. Okay, and it has some this 72 kilobytes of floppies and so on. So these are the ancient versions of Apple's and Macintosh. So they came up with this simple BIOS like operating system like DOS. Then there are a couple of efforts to have a better operating system for Microsoft. They came with this Windows 95, then NT, and so on. It goes like that. So this is an advertisement of just first PC, which has, not PC actually, this is 6502 was Commodore's processor, and these are memory slots. Most of them are memory slots. Memory was like that. These are memory slots. So now actually you know the rest of the story. After that we had different branches of operating system, the server, desktop, and embedded system emerged, and we have larger scales required. Larger scale computation is required, so that we have clusters and so on. So nowadays we have system on a chip, on a very micro scale computers, starting from there to the clusters of thousands of computers having different kinds of operating systems. And they have different requirements. For example, if you have a very small device, mostly you are interested in controlling hardware. That's why you need some real-time response. However, if you have large scale, you need large-scale data processing capabilities with large disks, I/O, and you spend most of the sophisticated coding exchanging data, migration, delivery, distributed computation, getting results, redundancy, and so on, and of course security. So this is another extreme, let me say. So we have now, instead of a single hardware or single CPU operating system, nowadays we have symmetric multiprocessing systems. That means we have multiple cores in the same operating system executing in parallel. Symmetric means they have equivalent power, and they are accessing the same main memory. Sorry, it's not same power, but same characteristics, let us say. They do not have to be same power. Also, we have alternatives, but those alternatives are not much popular, let me say, massively parallel processors where they execute code together. It costs a lot. So actually, if you can utilize the ultra super, actually, the thing is, I believe in the best supercomputer with the highest processing power is still an MPP, and it breaks most of the cluster-based systems. Okay, but the clusters are easy to maintain, easy to replace, cheaper, and that's why we need to do this inter-process communication, networking, and so on. Yes, our PCs are classified. If you bought a PC 20 years ago, it wasn't, but starting with this, which one? Pentiums. No, I forgot the cut point, but starting with, yes, Celeron, yes, actually Celeron. So I'm not sure about the year of that, but yes, it is SMP. If you didn't try to execute a program with 65 kilobytes of memory, or if you didn't use this diskettes, you are not old, okay? So these are one extreme, and actually, when we put all those computers in a single system room and connect with fast interconnected, you connect like InfiniBand, it is called a cluster, but also the geographical disposition is something important because of redundancy, because of locality of services. So for example, you need to install some servers in Europe, some servers in USA, some servers in Africa, and so on, and so that your service will be faster and better. In that case, you need to have this distributed computation. This grid-like structure, they also call this grid, turned into this cloud-based operations, and there are various applications like data warehousing, the distributed services like search engines and video streaming sites and so on. They are using this geographical distributed computers connecting to each other. And it has a completely different story because we have operating systems, and on top of operating system, we need to implement some distributed computation layer, so it gets more complicated. There is a course in our department called distributed computing. If you are interested, and you can take that if they offer it. In some semesters it is offered. So this is the embedded world. Embedded world is getting much more important. With IoT and so on, we had more sophisticated operating system and hardware is used because you need to connect it to the internet. So this MEMS-based systems, it can be as small as just finger. Whole system can fit into that. With this operating system, we turn back into history to our machines that have 8 kilobytes of memory, 64 kilobytes of memory, and very limited CPU. And there is no multiple cores and so on. So you cannot have this thick layers of peripherals and so on. Your program doesn't have a virtual memory. Your program has to fit the allocated slot. And you, in order to implement multitasking or some sort of interactive operation, you need to implement it on your own sometimes. Or you can use a real-time operating system with very small footprint. So the basic operation is just a simple task without any delay. You have to do that. GPU. I believe in 2000s they started having this very powerful pipelines for massively parallel operations. So instead of SMP, I talk about MMP. They inserted this MMP capable processors in order to fulfill the requirement for games and the computer graphics. Then they had this idea of programmable GPU later, I believe. Again, I don't remember, but in I believe it is 2000s. In the 90s, we used to have graphical processors, but we couldn't program them. So if you talk about programmable one, it is like 2000 something. So this is about the embedded operating system, which is completely a different area. Sometimes they use exokernels, that means only one task. They do only one task. Sometimes we have this shrink down versions of Linux or other operating systems into them. Of course, it is. So as you can program, the thing is, they were trying to sell in 90s this massively parallel systems as number crunchers, the supercomputers. So I'm thinking about this very expensive machines nowadays in your desktop working in a PCI card. So you are going to use it anyway. Okay, so this is about the history. If you have any question about the history, I can answer. Or I can have a simple introduction. So the Errol is going to take over from here. So let me just give you introduction of the next slide, and then let us have the break. Before that, do you have any questions? Kaç kişimiz var? 97. Hiç fena değil. Okay. This wasn't that.
Okay, well, let me just jump in here.
Okay.
Help Onur Hoca. So, like, based on the question, I also checked. It looks like the first GPUs, they emerged around 95, but the first actual GPU that is counted as the modern GPU came in 1999 as GeForce.
Programmable one.
Right.
CUDA and so on. Okay.
So it was initially built to aid rendering in computer graphics. But after, well, during the recent years, you know that it's commonly used to train and execute neural networks with large network sizes.
So any computational resource that you don't use is wasted. So actually, it's a good idea. Anything that can be programmed, you can write programs. So just let me give you this introduction of need for this exceptional control flow, and I'm going to have a break, and after the break, Errol can.
Okay, well, if you wish, we can just have a break, Onur, and I can just start with those slides.
Okay, I'm pausing, and I will see you next week in Monday lectures.
Okay, let's continue. So after talking about the brief history of operating systems and where the big picture is, now what I will do in this lecture is I will try to link this with what you have learned in computer organization. Okay, and actually the slides that I'll be using for this is from the same course, from the same book, because the computer organization book that we had, it also had a section on operating systems, and it was like in the original course given at CMU. They were both taught within the same course. So in computer organization, what we have learned was, we designed a full CPU, and the CPU was something that would continue to execute basically instructions over and over. It's like an engine. It fetches an instruction, it decodes it, executes it, and then in the end, then it would then come back and then read this next instruction and so on. Okay, so in this sense, when we talk about a program, a processor actually has there's a sequence for each program, which we call the control flow. Okay, and we have these instructions, and these instructions tell us the sequence of their sequence of execution. So this is the time axis. You first execute instruction 1, and then 2, and then 3, and so on. Okay, until you shut down. And within this, actually, you can see that once you start executing a program, then there is nothing that you can do to do anything. For example, imagine in this particular setup, you have a program, and you start executing that program, and then where do you check whether the user has pressed some keyboard? Okay, where do you check it? There's nothing. It's if you look at this, this is like the CPU, as you have seen so far. It's more like just a thinking machine which doesn't interact with the world. Okay, so in the original control flow, the only places where we do not follow a sequential execution control flow was in jumps or branches. Okay, and when we have a call or return, in which case we make it jump through that. But these are all basically these are all reactions to the program state, meaning that you always jump to the very same thing. It's encoded in your basically program, and hence there is nothing, again, the world, we don't care how the world works. Okay, now sometimes while in actual life, you also want to react to changes in the system state. What we mean by this is, imagine, in your program, maybe the data arrives from your network adapter. For example, imagine you're running some code, okay, which is supposed to read something, say or fetch something from a web page, from some other computer. It makes a request, and when it arrives, then it should be ready to fetch the data. Or when you maybe you have some data coming from a disk, okay, then you should react to this. Or sometimes, if you have an instruction that divides a number by 0, well, I mean, it will, you can, within the CPU, the processor, like when you do a division by 0, well, it will do things. Okay, you will get some certain flags open up, but it should continue as it is. So there is nothing that you do. Or when the user creates Control C, you want the program to react to this. Or sometimes, when the system timer expires, and this, we will see that the system timer here, it's just an alarm clock that will basically ring once in a while, and we will see that it's being used to switch back and forth between multiple programs. So what we need is a mechanism for exceptional control flow, meaning that there's this control flow that's defined by the executable. But what if certain exceptions happen? Okay, and This happens at all levels of a computer system. Like in the case of, I mean, at this time, you guys are all quiet, and I have this series of lectures, like in my slides. And what I can do is, I can go over them, I can tell them one by one, okay? And that's it. Now, this is the regular control flow. I have a control flow for lecturing, okay? But there is something that can break my control flow, okay? Can you guess what it is? Exactly. When you ask me a question, which can come at any time, then I should stop what I'm doing and then I should react to this, okay? And this is an exception. That's what we call, okay? And the same thing happens with the computer system, okay? So these exceptions means that, when these exceptions happens, then there should be a change in the control flow. For example, when you ask me a question, then, well, what I do was, I listened to you, I understood what your problem is, okay? I stopped lecturing, okay? And then I respond to your question, okay? And in the case of the computer, this is implemented using both a combination of hardware and also the operating system software that works in conjunction. So we have a number of higher level mechanisms. One of them is called process context switch. And a context switch, as we will learn in detail, means that, the first thing that you should know is, let me just introduce this. We will be talking about the processes. What the process is a process is a program that is being executed, or a program in execution. A program can be something that resides on your disk, okay? So a program does not mean that it is running. But a process is when your program starts execution, and when it's executing, then we call this a process, okay? And as I have discussed in the first lecture, when you have multiple, like one of the illusions that we do is when you're running multiple processes at any time, you run one process for a certain time, say 50 milliseconds, and then you stop this and you run the second one for another 50 milliseconds, and then stop this and so on. And all these things happen because there's a hardware timer that triggers, that rings, okay? And when that rings, then the operating system should stop what it's doing and then switch to the next one. So we call this a context switch, okay? Or they can be signals. Again, we will learn what these are in operating systems means. And for example, one way to generate signals is when you hit Control C, that sends a signal to your program. And we will see how we can handle this. Or some non-local jumps, again, like set jump and long jump, we will see that these can change. These are standard functions that are implemented by C runtime libraries, which can change the context of a running program. Again, we will see them in detail. So an exception is that you have some user code here, and you're executing your instructions one by one. You may be jumping, calls, returns, but it's always the same sequence of instructions. Okay. Now, when you look at the code, there's two parts of code. There's the user code. This is where your executables are, and there's the kernel code. Okay. And in the case of the user code, when you execute an instruction, let's call this I_current, and then an exception happens. This exception may happen like it can be divided by 0, it can be arithmetic overflow, it can be a page fault, it can be the IO request completes like a data coming, or or the user typing Control C. So when this happens, then we call this an event, and then an exception is basically thrown. Okay, when an exception happens, then you check the kernel how to handle this. Okay, this is so we have this exception handler, which is again a fancy way of talking about this, and actually similar to a function call. Okay, and then this exception handler code would be working. Okay, and then after that, then you have three possibilities. You may return to execute the current instruction, you may return to the next one, or you may abort. So in the case of, for example, my lecturing here, when I'm lecturing here, at any time, a question may come from one of you. Okay, I don't know who, I don't know what type of question it is. So this is one type of one exception. And for that, I have a handler. And that handler is basically stops lecture by I stop lecturing, and then I listen to your question, and then I process your question and I answer you. And then after that, I continue with, for example, the next thing in my lecture. Okay, that's one option. But there can be others like interrupts, exceptions as well. For example, right at this time, if the fire alarm goes off, okay, then what would I do? Well, if the fire alarm goes off, then it will create an exception. It will be a different type of exception. And for that, what I will probably do, I will quit the lecture and I will say, okay, that's it for today. We're ending and gone. Okay, I will not continue. And sometimes, like we also return to the current instruction, which, as we will see, will be used in handling exceptions such as page fault. Okay, and then it will move on. So when you think about, I asked you a question that what was an operating system code looks like, right? And is it like a while loop that constantly read and program and execute it and then move to the next one? Is it just a simple while loop, or what does it look like? Well, guess what? Like an operating system is actually a very different kind of software. It's not your regular type of application. What it has is, in this particular case, I will show you that it has an exception table. The exception table tells it's an array of addresses which point to exception handler code. Okay, for me, for example, these exception codes can be, there can be an exception for student questions. There can be an exception for my for fire alarm. There can be an exception for I don't know, something that's happening on my computer, etc., etc. So typically, in the operating system, we have this exception table, and then we have a certain code for each of these exceptions. So if it's exception type 1, then you execute this handler. If it's exception type 2, then this is the handler that you do. Okay. So and this is basically it's also known as an interrupt vector, and this is how an operating system actually works. Okay. And when we look at the exceptions, we can actually clarify this exceptional control, basically, system. We classify them into two. One asynchronous and the other one is synchronous. Yes, you will be able, like, for search, some of them it is possible, for some of them it's not possible. The exception table usually for each process, by default, you have an exception table. Okay, this exception table, as I said, some of the exception handlers, for example, exist for all the processes. For example, the timer exception, which triggers the context switch from one process to another one, it exists for all the processes in the system. Okay, but other exception handlers, for example, handling, for example, for control C, that can be specified by the user. Usually it has a default handler that's installed, but in your program, you can change this handler and you can write your own handler, and we will see this in the upcoming lectures. Thanks for the question. So with these, when we look at the exception control flow, there are two types of exceptions. There are the ones that are asynchronous or that are synchronous. The asynchronous ones are actually generated by external devices, which we call interrupts. Like, the timer is an interrupt. Usually it's like the network card, it can throw up an interrupt, or the disk, that it can also create an interrupt. Okay, so these are the interrupt. There's actually a pin on the CPU which sets it to high whenever that interrupt happens, and based on this, then the processor, the processor stops the current execution of the program and then jumps to the proper exception handler. Okay, so these are called asynchronous because since they are generated by external events, okay, you have no idea when it will happen. Okay, and then we have synchronous ones which are generated by the program. Okay, we will see that there are they fall into three categories: traps, faults, and aborts. Okay, you may already know what an abort is. When, for example, when you press say Control C, then maybe it should abort. Or when there's a page fault, then you know what we have to do. And there's traps, which I will discuss in a second. Okay. So as I said, the asynchronous exceptions, they're asynchronous because they're generated by something else beyond your program or your processor. Okay, so they're usually set by the processor interrupt pin, and when it's executed, then the handler returns to the next instruction. For example, your execute program, and suddenly a data arrives from the network card. Okay, then what you should do is you should go ahead, fetch it, maybe write it in some portion of the memory, and after that, then you should come back and continue your execution. Okay. And another one is, for example, a timer interrupt. In the case of a timer interrupt, for example, every few milliseconds, the external timer chip, okay, it triggers an interrupt like an alarm, okay, and then the kernel then looks at this, and then it stops the current process that's running, and then maybe we switch to something else. Or it can be an I/O interrupt from an external device. For example, when you hit the Control C at the keyboard, it means that you're sending an interrupt to that, okay, or the arrival of a packet or arrival of data. So these are all interrupts that are generated by external means, and we have no control over when they would happen. And then there are synchronous exceptions. These synchronous exceptions, they're caused by events that occur as a result of executing an instruction. Okay, so this means that these are generated within the processor because you're executing a particular program. The first one, what we call, is a trap. A trap is something called, it's intentional, and we will see basically why we need traps. They're intentional, and examples are system calls or like breakpoint traps, and it usually returns to the control to the next instruction. And at this point, what I will do is I will maybe go, let me see, okay. So we will discuss basically how these traps are being done, what a system call is, okay? Now let me just focus on the other ones, the fault, okay? The faults are called, it's an exception. For example, a page fault is a prime example. They're unintentional. Why do we have a page fault? A page fault happens because in our virtual memory system, we are trying to access a memory location that is not yet brought into the physical memory. Okay, meaning that it can happen. It's not something that my program intends to do, but but it will happen, and possibly it is recoverable. Okay, for example, in the case of a page fault, it is recoverable. What it means is, after a page fault, I should maybe go ahead and read the particular disk block from the disk, and then bring it into the memory, and then continue. No. And by the way, if you have a question, please speak up, because I'm not looking at when I'm doing these presentations in full screen mode, I'm not seeing your chat questions. Okay? So the answer for that is no. So in the case of a page fault, we will return to the current one, and it is recoverable. But there can be, for example, protection faults. When you make a null pointer access, okay, then it's a protection fault because the address pointed by the null pointer points to a page that you are not supposed to access. So in that case, that's an unrecoverable fault or floating point exceptions, okay? So when you have a fault, you may either re-execute the faulting or the current instruction, or you may abort. It depends on if it's, for example, if it's a segmentation fault, then you're an abort. If it's a page fault, you re-execute the faulting instruction. And then there are aborts, which is unintentional and unrecoverable. For example, if you have an illegal instruction in your executable, which can happen, then it is unintentional, but it's still a synchronous exception because it is caused by the process, by your process, and it is unrecoverable, right? Or it can be, you know, a parity error from your memory access, it can be machine check. So when that happens, then you abort the current program. Now let's look at them in detail. So here is a simple example where I have a program and I have declared a variable here, okay, a of 1000, and in this location, in this line, I'm setting the 500 element to 30, okay? So let's assume that when I do this, this is the instruction, which is I'm moving, you know, 0xd, which is 13 in hexadecimal, into this address, and this address, this 0x8049d10, this is the address of A50, okay? So I'm moving this, so this is the execution. Now assume that this particular address is not yet in the physical memory, and it is still mapped onto the disk. Then what will happen? Well, in my user code, when I'm executing this move instruction, then it will create a page fault. It will create an exception. And when that page fault happens, then I have this kernel code. Again, we will learn about the details of this, okay? And let's see, have I started recording, by the way?
Yes, Hocam, it's recording.
Yes, it's recording, okay, good. Because I cannot see this. So in this case, when I copy, then the kernel code will then copy this page from disk in from the physical memory, okay? And after that, it will return, and then it will re-execute this move instruction again. But guess what? In the second, in this re-execution, then it will not cause any page fault, and it will execute fine because this time it's in the physical memory, and then you will move on. So this is a case where I have a fault and it's recoverable, and then I move on, okay? So in this case, I'm trying to access A5000, which is somewhere in the memory that I'm not supposed to access, okay? So this is an illegal memory access, and again, this is the code that I do. So in this case, it's user code. You have a page fault, okay? But when I check this at the page fault, my kernel will say that, well, that particular that particular address location, it doesn't map to anything. You're not supposed to access that, okay? So it's an invalid access, or for example, if you had a null pointer, it will be again the same. And as a result, then it will signal the process and it will abort the current execution of the program, okay? So this, in this case, it will be essentially a segmentation fault, okay? So in this case, you know, as you will learn later, you know, it will actually send a seg-v signal. Again, you will learn what the signal is later, and then the process will exit with the segmentation fault. And then there are system calls. Okay, what the system call is the following. Let me just, will actually, for this particular case, I will go with this library example. Of course, you're far from our library, but, you know, I'm pretty sure that in your, years so far, you've been to the library, and there's this reference section, right? And in this reference section, you can see that there's a set of books here, and there's some guy guarding here, guarding in front. And what he does is, you know, they put some of the books in here. Most of the other books are in the open shelves, but some books are in the reference section, okay? And there's this desk that prevents it to get in, but there's this guy that's sitting in here. Now, you know, which books do they put into this section? Do you have any guesses? Exactly. So the ones like the textbooks, okay? And they put it here. And why do they put it here? It's because, well, these books are in high demand, okay? So you don't want anyone to check them out. You don't want anybody to misplace them to some other place. I mean, if they imagine, for example, this is a trick that, I'm pretty sure you guys, the students would do. If I put the textbook here in the library, into some open shelf, I know that some students who wants to access them at all times would misplace them to some other shelf, okay, and then use them as they are, while all the other guys will not be able to find it. Okay, that's why they put these textbooks, for example, into this section. And but the fact that they put them into this reference section doesn't mean that you cannot access it. You can access it, but you have to go through this guy at the reference section. What you should do is, there's this form usually. You fill in this form. You say that, I want this book. Maybe this, here's the name, here's that. And then, you go there. This guy is for most of them, he's not doing anything, right? He's basically just sitting there. You fill in the form, and then when he checks it, and then he stands up, he goes there, he picks the book, he hands it to you, and then sits there again, right? So this is actually how the operating system works, okay? And in the case of a computer system, the instruction, we have a instruction set, right? And we have seen in the computer organization what those instructions are, like move instruction, blah, blah, etc., etc. Now, some of those instructions are privileged, okay? What they mean by this is those instructions, they access the hardware directly. For example, the halt instruction, okay? It's an instruction that is privileged because I don't want some, guy who would just create a 1-byte executable which containing that instruction and then run this on its own executable and then shut down the whole computer system. I don't want this. Like, I don't want users to execute at that basic level. But so what I would do is, or for example, when you want to access the like disk or other things, I want user applications to access them, but in a controlled way. Okay, just like the books in the reference section. Okay, so with these instructions, that's why, in the case of an operating system, the operating system is actually this guy that is sitting at the reference table. Okay, and what you do is whenever you need to do something in the privilege instructions, then you have to tell this guy, you have to fill in a request. Okay, you wake this guy up, and this guy is actually running exception handlers. Okay, he will carry this out for you, but when he's doing this, he will also be checking whether you have the right to do so. Okay, for example, in the case of memory access, remember that we had this protection fault, right? What it did was, it checked whether you had access, you had privilege to access that particular memory location. If you do not have, then he would say no, and he will basically abort you. And the same thing happens here. Maybe, for example, certain books, maybe like the textbook, for example, for say for this course, may be available to only the computer engineering students, okay, but not others. And this guy will check this through that, and this is the same thing that is happening. Now, what they call like this service that this guy coming from here and doing those, executing those privileged instructions for you, that's called a system call. Okay, a system call is basically is the way of a user process asking the kernel to carry out some privileged instructions on behalf of him. Okay, so if you're here, okay, if you're a student in this part, you are the user process, and then here it's the kernel guy, and this portion of this whole thing, that's the kernel space. And when you fill in this form, you're essentially putting the arguments in a system call, okay? And then when you do this, now remember, this guy is sleeping all the time. He's not executing. You fill in this form that's basically putting the arguments in a system call, and then you ring. There's this ring to wake him up, and then you just ring, okay? And this creates an exception. This is called a trap, okay? When you ring this, then this guy wakes up, takes the form from you, carries this out for you, comes back, returns it, and in the meantime, you're frozen. You don't do anything, okay? And in that time, basically, you're put to sleep. And when the reference guy carries this out, then he would again go back to sleep until another request comes. Okay. Now let's come back here. So traps, it's an instruction. Okay. And with this instruction, what you do is you basically ring the guy and you tell him, execute this particular handler for this, okay? And here are some examples. For example, whenever you're trying to read a file from the disk, okay, there is a handler, and this is the system call. This is just another function, except that this function has to be executed in the kernel level by the kernel. And it is a certain number. This is number 0 means I want to read a file, okay? Number 1, it's write a file, open a file, close a file, or get information about the file, or fork to create a process, execute a program with exit. You will learn all about this, or kill. So these are all different system calls with their own unique IDs. So they will all appear in that exception table or interrupt vector that gets sweet. Okay, and what will happen is the following. For example, when you have, here's an example of opening a file. And when you have a file like this, and you want to open, you have to make a system call, because accessing the disk, that requires privileged thing. Actually, accessing any hardware directly is a privileged instruction, and hence then we need to do this through the kernel and through making a system call. And the way it does is, in this particular case, exactly. So in this case, this is like a let me just go through this. So what I do here is so there's a instruction that's called syscall, which is 0x05. Okay, and in this instruction, if you remember, in this particular, when we are trying to open a function, and you can see that when you do an open here, this open, you may it's this makes a function with the system call, okay? But the system, this is a library function in C, okay, that makes this call, okay? But when you look into the code, you will see it's __ open function, which actually makes this system call instruction, which is syscall, okay? And when you look into the implementation of this __ open function, which you can see here, you will see that it is saying that I will make a trap, okay, a system call, and it will be of type 2. Why is it type 2? Because I want to open this. It's telling me the type of the system call. And once you put this in here, and before this, it also puts all the other arguments like the file name, options, okay? All these things are placed into the proper locations in these in the upper part, which is like ... okay? And then once you put this, then what you do is you do a system call. When you make this instruction, when you execute this instruction here, then it creates an exception. What it means is, after this, we have this compare instruction, but we don't execute this. It creates an exception, and then it jumps into the kernel code to open the file, okay? And it executes this, it's like a function call. It executes this handler, and when it's done, then it returns back, and then executes this compare instruction that is next in this. Okay, and if there is an error, then usually it's also put as the return value in, as an error no, and you can see that these things what you see as function calls, sometimes the actual function call, like in the assembly level, this is called a trap, okay, which triggers the system call. And then you have this open file name options. This is the system call. This appears as a system call, but this is actually a higher level implementation of open as a library, and then which in return calls this underscore open function, which again makes this call. Is that clear? So there is multiple layers. So at boot time, like the hardware supports that, there's this, what the hardware supports is this instruction, okay? And it says that, it actually, you can see that this 0 to, this is an index to a function pointer table, okay? And the operating system fills in this read file, like what it wants to do with number 0, number 1, okay? It fills in these handlers in here, so at boot time. And after that, it will continue to execute them. You may write your own operating system when you say, when the type of 0 happens, I don't want to read a file, but what I want to do is I want to close a file. So let's move on. Okay, so what we mean by a function, the system call is, whenever you have like applications and we want to prevent direct access to hardware, which you want to do. I don't want to have different, like I don't want the programs to access the disk direct. I don't want the programs to access the memory, to access the network card, okay? Because if you allow them to access them in an uncontrolled way, they can, access other people's like data, they can crash the system, etc. So all these things, like or the halt instruction, we want to prevent direct access. And so what we do is, nevertheless, they have to do this to like read write memory, they have to access files, they have to access the network, etc. So basically, we have the processor actually runs it 2 different levels. So when it's executing instructions, it runs at the user level. It can execute instruction in the user level, or it can execute the instructions in kernel level. Actually, there are multiple levels, but at this time, this is the best that you can handle. In the user level, the processor is not allowed to execute privileged instructions, even if you have them included in your. Only when the processor switches into the kernel level, which is again, the switch is again handled by the operating system. And so you cannot switch, at your own will. Only in the kernel level, then you have the right, then the processor can execute privileged instructions, okay? So as I said, these privileged instructions are all the instructions that allow you to access the hardware, okay? And your user applications, they do not include any privileged instructions, and only the system call codes, they include the privileged instructions, okay? Because they are the ones that are allowed to access the hardware. And in this case, like in our sake, and when we look at this, the operating system actually provides an API, okay, in the form of system calls. So the set of system calls that an operating system provides, basically, this is the interface that is provided to the user applications, okay? So it allows the user applications to access the hardware in a controlled way. And with them, this in the reference section, the handler code, this is the guy that's sitting here, that's sleeping most of the time. So this is the handler code. And moving in here, that's a privileged instruction, okay? And this is the hardware, the books here, meaning that, and you user, you're the one outside this basically privileged the reference section, you're the user. Well, I mean, like the passwords and other things, they're actually implemented at a higher level. The system calls operate at a very low level, okay? For example, changing the page table, that requires that. And let me just go over with this, like this coverage, and then we'll come back to your question, okay? So like what we mean by that, the system calls, they provide process control, that you can load a process, you can execute a process, you can abort a process, create or terminate processes. They're all, we have system calls for this, and you will start learning them right away. Or file management, creating a file, deleting a file, open, close, read, write, seek. These are all, again, system calls. Device management, requesting a device, releasing a device, read, write, reposition, or some maintenance information like get, set time, or get, set system data, or some communications like create, delete communication connections, send, receive messages. So these are all things that are provided at the level of system calls, okay? And the operating systems actually, the set of system calls that an operating system supports, this is the API for that one, okay? And the one of the ones like that's important is POSIX. And POSIX API, this is defines a set of system calls, and it's a standard, meaning that if somebody says that their operating system is POSIX compliant, it means that all those functions with that particular, all that API, system call API, is implemented in that. For example, the POSIX API is supported by most versions of Unix, Linux, different BSD or Mac OS X. Okay, so Mac OS X is, for example, it's a different operating system, right? So it's implementing is the same. It's implementation of the same system call is very different. Okay, but what's nice is when you write your code, and if you only use the POSIX API, then you can compile this on Linux or Mac OS X, and it will execute fine. Okay, because what it does, I want to open a file, it passes. What happens underneath, it doesn't matter. Okay, so this is a standard. But for example, in like if you go to Mac OS X, it supports the POSIX API. Plus, it supports other system calls, okay? So that means that if you use those functions, those extra system calls, then your code is now no longer portable for Linux. You have to do some extra things. This is true for all the other versions. Or for Windows, there's this Win32 API, and so on. And what we will be using in this course is we'll be going over this POSIX compliant system calls like open, read, write, close, wait, exec, for, exit, and kill. And similar versions are also appear in Windows API, except that they have slightly different names and etc. But the concepts actually apply pretty well. So in the POSIX, again, this is a standard, this is like a Turk standard. This is like this is IEEE standard. Okay, and there's it's based on C language, and in this POSIX standard, it defines a set of system calls, and also as well as some system programs. So this is system programs. Basically, they provide. It's not like you should differentiate from a system calls from a system program. A system program is actually a program at the user level. It's a user program, except that you're supposed to provide them in this if you want to comply for this one. For example, LS. Okay, this is a system program that for example, that your operating system should support if it wants to be POSIX compliant. And this is what comes. But the nice thing is, for example, maybe you'll be doing similar things in your assignments. The LS program, there's an implementation in, say, Linux, right? But you as a user level, you can write your own LS to do the same thing in your own code because it's a user program. And what LS does is it makes the proper system calls to access the disk and then display you that proper information. And actually, there's nothing special about LS. Okay, so ls is just another yet another one, except that in order for usability, basically it is included in this POSIX standard. And this again in the Win32 that has this, and I have also a link for this complete specification for that. And it's very similar with that one, but it's actually pretty complex, very complex, and there is really no complete specification because there's if something runs on Windows, that's fine. Otherwise, they don't care. So that's it for today.